I'm Ian Somerville, and in this video I'm going to be talking about issues of availability and reliability. In a previous video I talked about the concept of dependability as a composite system property that's an amalgam of four other properties: the system availability, reliability, safety and security. Simplistically, availability is the ability of a system to deliver services when requested to do so, and the reliability is the ability of a system to deliver services correctly. There is a more formal definition of these terms which takes into account the fact that they can only be defined in a specific operational environment. The formal definition is: reliability is the probability of failure-free system operation over a specified time in a given environment for a given purpose. So this kind of takes into account the fact that if you're using the system for something it's not meant to be used for, you won't get the same level of reliability. The formal definition of availability is a probability that the system at a point in time will be operational and able to deliver the requested services. Now, what's very important about these definitions is that they are expressed as probabilities. Therefore, availability of 0.999 means that the system is up and running for 999 out of 1,000 time units. A reliability metric we use is probability of failure on demand. A probability of failure on demand of 0.0001 means that 1 in 10,000 demands will result in a system failure of some kind. It's obviously the case that availability and reliability are related. If a system is not available, it's obviously not delivering its services correctly. But in fact, it's usually helpful to think of these separately. It's actually possible to have a system with high availability requirements, that is, to deliver services when requested, but low reliability requirements, so that it may frequently fail. This is possible if the failures are not damaging to the system and it's possible to recover from them quickly. So, for example, if a request for service is made, the system fails, the failure is detected and corrected, the requester of that service may never know that a failure has occurred. We normally express availability as a percentage. And availability is particularly important in a world of web-based systems where people may access them at any time of the day or night or any day of the week. The problem, however, with expressing availability as a percentage is that it can be misleading. We can say a system has an availability of 0.999, so that's one failure in every 1,000 units. But if that failure occurs during the day where there's a large number of system users, it's much more damaging than if it occurs, say, at 2 o'clock in the morning where there are many fewer users. It's also the case that if you have a very rapid restart time, so that after failure you can get back up and running in a couple of seconds, that's much less disruptive than if you have a long restart time and users are locked out of the system for that time. So the availability metric can be a bit simplistic. It can give you a misleading picture of the practical effects of a system crash. We typically use two metrics for reliability: the probability of failure on demand, which is the chances that when a demand is made for some kind of system service, the system will respond correctly, or the rate of occurrence of failure, which is the number of failures that happen over a particular time period or over a given number of transactions. We use these two metrics because the appropriate metric depends on the type of system which you are specifying, where you're trying to say what reliability is required. So if it's a transaction processing system which is processing potentially thousands of transactions per second, the rate of occurrence of failure is the right metric. On the other hand, if the demands for service are intermittent, say in a safety system that is only triggered in the rare event of things going wrong, the probability of failure on demand is the right one. We don't see enough failures over a period of time to use the rate of occurrence of failure. It's helpful when we're talking about reliability in particular to use quite specialised terminology and to think about faults, errors and failures. Faults are static characteristics of a program. They're things that are wrong in the program. Say you have initialized a variable to 0 instead of 1. An error is a dynamic characteristic of an executing program. It's where the state of the program is not what it should be. So therefore your initialization statement has been executed and the variable that you have initialized has the wrong value. Of course, it's possible that your initialization statement will never be executed, so therefore the incorrect state never actually occurs. If the incorrect state leads to a system failure, that's something that's externally observed. It's something that happens outside the system. So a value of 0 may result in an incorrect value being computed and presented to the user. What we have is this cascade from faults, cascading to errors, cascading to failures. And when we have multiple systems involved, we can say faults, errors, failures. These failures lead to further faults in an enclosing system, errors, failures, and so on and so forth. It's not necessarily the case that faults in a program, bugs in the program, will necessarily lead to system failures. In some cases, the faulty code is never executed. In other cases, the error is transient. The state is incorrect, but then a further computation is made which corrects that state before it results in a failure. Similarly, errors do not necessarily lead to system failures. There can be built-in error correction mechanisms which correct the state before it has any adverse effect. Or there may be protection mechanisms in place which mean that the effects of part of the state being incorrect do not propagate to other critical parts of the state. The notion of faults, errors and failures, and the fact that failures derive from faults at some stage, allows us to think about the approaches that we can use to achieve system reliability. There are basically three approaches. These are fault avoidance, fault detection, and fault tolerance. Fault avoidance is the use of development techniques in a development process that avoids the introduction of faults into the program in the first place. So we may use, for example, formal methods as part of our process, which helps us avoid certain types of specification error. Fault detection and removal is where we use verification and validation techniques to discover faults and to remove these before the program is put into operational use. Obviously, program testing in general is part of fault detection, but we may also use more specialised techniques such as static analysis to discover errors in a program. And fault tolerance is where we use runtime mechanisms to detect erroneous state which results from a fault and to ensure that that does not lead to system failure. So the faults exist, but the system tolerates these and does not fail as a consequence of the faults. In summary then, availability is the probability that a system will be in service when a request is made. Reliability is the probability that a request will be serviced correctly, that is, give the right answer. Software faults lead to state errors, which lead to system failures. And the mechanisms we use to achieve reliability are fault avoidance, fault detection, and fault tolerance. You can download the slides that accompany this video from my SlideShare account.